Ahmed, can you also get me the solution link for this the last problem? This,
Oh,
last problem. Yeah, last problem, and also the
okay.
question link for the previous problem.
So I sent
That's
it
the
on
last
the
one.
chat. They are in the same order. Yes, it's sent here after the submission of the last problem. Okay, just to not make things messy in the chat. Can you see it at 6:04 a.m.? No, it's my client. So it's after the AdCoder submission. I sent the question link.
Okay.
Okay, and here is the submission. I sent it. And actually, from the submission, you can open the problem directly. So here's the submission.
Okay. Okay.
Okay, any ideas for this problem? Any ideas? Okay, let's explain it. So you are given a tree with n vertices and obviously n minus 1 edges. And for each valid I, there is an integer a of I written on the ith vertex. So basically, we are given n vertices, and each vertex has a value written on it. Okay, and also for the n minus 1 edges, we have a value b of I written on the ith edge. Okay, so we have a tree with with vertices having values and with edges having values. Okay, and we want the following condition to be satisfied for each vertex and each edge that's adjacent to that vertex. So we want the value of the vertex to be greater than or equal to the value of the edge connected to it. Okay, and in order to achieve that, we may perform this operation in a number of steps. So the operation is we can swap any two different vertices. So we can take vertex 1, vertex 2, and then swap the values of them. And we can swap the values of any two edges. And the last operation we can do is changing the value of any vertex to any value we want. Could be infinity or anything. Okay. Let's try to make an example here. Let me try to get the better one. Okay, this should be okay. So here is some tree with six vertices and 5 edges. So let's have some arbitrary values here. And another 4. And here 1. So the numbers are too small. Here it's these 3, 2, 3, 1. So here I have a tree, and each vertex has a value and each edge has a value. So we can swap the values of any two vertices and the values of any two edges and the values and we can change the value of any vertex. But here's the thing: we want to calculate the minimum number. After we change the value of any vertex, we pay 1 coin. So we want to calculate the minimum number of coins I should pay to satisfy the required condition, which is the value of each vertex should be greater than the value of the incident edges. Oh, okay. So here let's take this edge, for example, which has 4. So this edge should be okay. So this vertex should be okay because it has value greater than all the values of its incident edges. So 4 greater than 2, 4 greater than 3, 4 greater than 1. Okay, but here, okay, this is right. But here, this is wrong. So this tree is not possible because 1 is smaller than 2 and smaller than 3. So we want to change this value. Okay, we could swap it with 15, right? So we could take this 15 and this make it 1. Okay, so this will be okay and this will be okay because 1 is greater than or equals to 1. But here 2 is not okay. And here we got to a point that we cannot do any more swaps because if we swapped 2 with 4, okay, we got this vertex right, but this having 2 is also smaller than 3. So it's not okay. So let's observe here some observations. Let's do some observations here in our editor here. So we said we have n nodes and n minus 1 edges. So let's put the values of the vertex in an array of size n and the values of the edges in an array of size n minus 1. So let's call the first array A of size n, and the second array B of size n minus 1. And let's put the values of this array. Okay, so A1, A2, A3, and so on. B1, B2, B3, and so on. Okay, A of size n, A of size n minus 1. Okay, so here we know that we could swap the value, we could swap any two values in these two arrays, right? So we could swap A1 with A3 and so on. So this actually the same meaning as we can order every array at any order we want, right? Because if we can swap any two values, then we can order this array as we want. We can sort it, we can make anything, okay? So actually we can, and this have no cost. We don't pay coins for swapping any two values. So we can actually sort this array in increasing or decreasing as we want. And also we can sort this array increasing or decreasing. So let's go back on the tree and see let's erase. So let's have an empty tree here, and we have two arrays that have the values of A and B, and we can put the so what it means by ordering the array as we want, it's the same thing as putting the values as we want in any spot we want, right? Because if we have 1, 2, 4, 15, 3, for example, anything. So here are 6 values. We can put these 6 values and distribute them in the nodes as we want, right? And then we have the edges, let's call them. So let's actually sort this. 3, 4, 10, 15. Okay, let's have the values of the edges and also sorted. So let's make them 1, 1, 2, 4, 10, also 11. But they should be less. Okay, so these are 5 values and these are 6 values. So now we want to distribute them such that we want to distribute them in a way to decrease the number of changes as possible. So we don't want to change, so we can pay 1 coin and change, for example, this one to 10 or 100. But we want to minimize the number of changes as possible. So let's think of an optimal way. Let's take a leaf and then put the greatest value in it. Okay, so let's take a leaf, any leaf, and put 15, for example. And then it's clear that the greatest value for the nodes would take the corresponding greatest value for the edges in it. Because if I didn't take the greatest value here, and for example, if I took 4 and put it on this edge, then I'll have 10 put on another edge. And this another edge would have a smaller values of corresponding nodes, right? So I'll put here 15 and put 10. Okay, and then so since I have the greatest value of the edges here put on this edge, then I'll take the second greatest value of nodes and put it with this edge. Okay, so then I have 2 remaining edges. So I'll take the second 2 edges from the greatest ones I have so far and put. And then, so the greatest one here, which is 4, I'll put 4 with it. And then the smallest one, we'll put 3 with it here. And then and so on, we'll continue this way, and 3 we'll put with it 1 here. So we'll have only 2 left, 1, 1, and then 2, 1. So we see here that this way we got a good tree. So all conditions are satisfied, and we paid 0 coins. So this actually should be the minimum value we could get here. We shouldn't change any value from there. So let's summarize what I did exactly to make it easier. So first, let's make it abstract here. So first, I sorted the array. So let's make this sorted in decreasing order, not increase. Okay, so AF1 is the greatest value. So first I sorted the 2 arrays, and then I got the greatest value from the first array, which is A. So I put A of 1, and the edge with it, I put B of 1, right? So I took the greatest with the greatest. But be aware that B1 should be also connected with another node, right? So how to okay, so this corresponds to an edge. Okay, so now I'll put B1 with A2, right? And then A2 should be connected to an edge. So I'll put A2 with B2 and so on and so on, and A3. So if I put it that way, then I'll always have the greatest values with the greatest values and smaller values with the smaller values, because it's not optimal to take, like, for example, A1 and put it with B3. So that should be okay for A1, but it shouldn't be okay for A2 or A3, because if I took A1 and with B3, then I'm left with a very great value in the edges, and I'll have to put it with a smaller value in the nodes, right? So I'll make it this way. So here, B2, A3, B3, and so on. Did you get how can you form? How can you do this tree now? So so now we are supposing that so we are not counting any number of coins now, and we didn't actually get to the actual solution of counting the number of coins. But now we made sure that this is the optimal way to rearrange the values of the nodes and the edges to achieve the minimum number of changes. Okay, do you all agree with this distribution? Okay, I think yes. So now after this distribution, we have to check the condition. Okay, so as I said, this is the optimal distribution. So after making this distribution with whatever values we have, okay, so whatever values we have, we'll make this distribution because this is the optimal one. So to check how many changes we want to do, we want to make sure that A1 is greater than B1, and also A2 is actually greater than or equal. Right? So A1 greater than or equal B1, and A2 greater than or equal B1. Okay, so this is an edge between these two nodes. So A1 should be greater than or equal A2, B1, sorry, B1, and A2 should be greater than or equals B1. Okay, next. So next to have A2 should be greater than or equals to B2. B2. And A3 greater than or equals to B3. Okay. So and so on and so on until we reach A of n. Yes, okay. Until we reach A of n greater than or equal B of n minus 1. So until we reach that the smallest value in the nodes should be greater than or equal the smallest value in the edges. Okay. So let's minimize that. So if I have this is if I have A1 greater than or equal B1 and A2 greater than or equal B1, so and I know that A1 is greater than B2 because it's before it in the array, right? It's sorted in decreasing order. So A1 is greater than A2, and I'm saying that A2 is greater than or equal B1. Then for sure A1 should be greater than B1, right? Because the smaller value is smaller than the smaller value between A1 and A2 is greater than B1. So then the greater value should be also greater than. So I don't want to check this. Okay. So here I'm actually only checking A2 with B1. Okay. And here the same thing goes. Actually, I did something wrong here. It's B2, right? A3 with B2. So here the same thing goes here. So A3 is greater than or equal B2. Then for sure A2 should be greater than or equal B2, right? Then I don't want to, then I don't have to check this. So I'm left here with only two checks, which is I'm checking A of I is greater than B of I minus 1, right? So A of 2, I'm checking if it's greater than B of 1, and A of 3 is greater than B of 2. And then after this, A of 4 is greater than or equal B3, and so on. So I'm only checking if A of I is greater than or equal B of I minus 1. So to make things look easier, after we have got what we need here, I'll in the explanation. So in the actual solution, I'm sorting A1. I'm sorting A and B in increasing order. Okay. So A1 is the smallest value, B1 is the smallest value, and so on. So instead of doing that, instead of checking each value of A of A of I with B of I minus 1, I'll be checking. So now what does that mean is that I'm starting from the first value of the edges. So I have here a check between B1 and A1, and a check between B2 and B3. And then at the end, I'll be having A of n and B of n minus 1. So at the end, I'll be left with A of n not checked with anything, right? Because I'm saying that I'm checking A of I with B of I minus 1. So A of n will be checked with B of n minus 1. So, and then A of n minus 1 will, sorry, so actually this was in sorting in reversing order, okay? So after reversing it and sorting in ascending order, then I'm just now checking A of 1 with B of 1, so the smaller value with the smaller value, and so on, until I'm left with A of n not checked with anything, right? Because I said if A of n minus 1 is greater than B of n minus 1, then of course A of n is greater, right? And again, if A of 1 is greater than B of 1, then of course A of 2 is greater. I know that reversing the array here made it confusing, but we'll revise it and it will be easy now. So now I've checked every corresponding element from A to B, and then A of n, it's not important to check it with anything. Okay. Did you get now what I'm doing exactly in this problem? Did you get, I want to make sure that you get this part, that I'm after sorting in increasing order, I'm checking only the first n minus 1 elements from A with the first n minus 1 elements of B. Okay. So what if after checking all the first n minus 1 value, so now A of n is not important, okay? So what if after checking the first n minus 1 values of A with the first n minus 1 values of B? So what if I found A of 3 is smaller than B of 3, for example? So now it's not possible to do it without, so after making this configuration and checking and found some condition false, then it's not possible to form this tree without changing the value of A of 3, for example. Okay, so to check, we want to minimize the number of coins, and this solution suggests a binary search. Why? Because let's look at if we made, for example, 5 changes. So if we made 5 changes to the array A, what do you think the change should be? So should I only change the values that are not corresponding to the that are not that are not making the condition true with the corresponding values, should I only change these values? No, because if I found, so if for example, if I found some values and changed them, I might I might change many values, but instead I could change only the smallest 5 values and make them very 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 big, because I could change any value as I want. So if I made 5 changes, then I could change from A1 to A5 and make them infinity, right? And after making that, I'll be sure that these 5 changes will be okay with any value, with any corresponding value of the edges. Okay, so for example, let's take one change. Let's take an example of an array here. It's 1, 2, 3, 4, and here be, yes, 4, 4, 5, 6, 7. That's it. So after ordering them that way, actually it's clear that it's not possible to achieve without changing, right? So after checking this, this is not okay. So this is not okay. This is not okay. This is not okay. This is not okay. Actually, all of them are not okay. Let's make this greater. Okay. So this is okay, and this is okay, and these are not okay, right? So you would say now that I want to make 3 changes, right? So 3 changes would be optimal. You would say that 3 changes would be optimal to make this array possible. So make 2 a very large number. Let's make it. And that would be okay, right? Yes, that would be okay. But actually observe that there is an extra element that I didn't use in this array, right? So I can only make 2 changes and then take this element and put it here, right? So I can only make 2 changes. So make this 100, 100, and take this 10 and swap it with 2. That's it. So I made 10 changes and it looks okay. 10 what? I made 2 changes and it made the array, it made the tree possible. Okay. So how to achieve this minimum changes? Let's again observe. That if 2 changes is possible, then of course 3 changes would also get us to a good solution, right? So if I can make 2 changes, then I can make 3 changes. Of course, this is not optimal, but 3 changes would get us to a right solution, right? So, and of course, I can make n-1 changes and make all the values infinity, and then it will be okay. So this is how I got to a binary search, because if I found any value that's not possible, then I'll just go to a higher value, and if that higher value is possible, then I'll go to a lower value, right? So until I find a certain value that I cannot go lower than that. Okay, so here in the binary search, I'll first, for example, I'll try 3 changes. Okay, and then 3 would be okay, right? So the next step, I'll try 1. So I'll divide 3 by 2, and then I'll go to 1. So 1 will be not okay. So now I have 3 okay and 1 not okay. So I want to go higher than 1, but I want to go lower than 3. So I'll go to 2. So 2 will be okay, right? So let's now see how to verify that certain number of changes is okay. So let's see how to verify that X is okay. How to check that? So let's go back to our original array. So how to check that X is okay? But but I said that I have an extra value here that I want to make use of. Okay, so it's clear that whatever x is, I want to change the first x values. Okay, so let's let's say x is 2. So I'll be changing. So the best strategy is to change only the first two values with some infinity. Okay, let's call it inf. Okay, so now I changed the first two values with infinity, and that means that these first two values would go to the last places in the array, right? Because um, since I have these two values infinity, then I can compare them with the last values in the edges, right? And it will always be okay, right? So I should put this here, right? And then compare these with this, right? Um, so let's compare while they are in place. So since these two are infinity and we want to make use of them, so we'll remove these two with the last two. So they'll always be okay, right? So I remove these two with the last two, okay? But then, oh, what's I should have an extra value here, which is 2. Okay, sorry. Okay, this is 5, these are 6. Okay. So now I remove these two infinity values with these two last values. Okay. Actually, I think it's not valid here. Hmm. Actually, 2 is not okay, right? Okay. So yes, 2 is not okay because I cannot change these two. Okay. So after taking the last two of edges with the first two infinities, then the first value I check here, which is 2 and 4, they are not okay, right? So 2 is not okay. But let's take, for example, 3 and again change the first three values to infinity. So then I'll take the first three infinity values with the last three values here, right? Then I'll continue our checking. So the first value with the first value, the second value with the second value, and so on. Okay. And then here everything satisfies the condition. Then 3 is okay, right? But as I said, for 2, it's not okay because I was having 2 here and it wasn't satisfying this condition. Okay. So how to check this fast? So how to check? So should I actually delete the first element, then the second element, or delete these three elements with these last three elements? No, I don't have to do that. I would only have to check I would have only to leave the first three elements and start checking from the fourth element. But then checking until n minus 1, until exactly n minus 1, because the last value shouldn't be checked. So I'll check until n minus 1, but starting from the first value. So it's something like 2 pointers. So I'll start here with let I be the index of A and J index of B. So I'll start for this particular example with x equals to 3. So I'll start with I equals to 3. So it's 0 based index, okay? 0, 1, 2, 3. So I'll start with I equals to 3 and j equals to 0, right? So I'll check I with j and then increment I and then check 4 with 1, okay? And then check 5 with 2. But actually, I won't check 5 with 2 because the last element is not checked. Okay, so I checked 6 with 6 here, and 9 with 7 here. That's it. And if it's okay, then it's okay. And then I continue my binary search. Before jumping into the code, did you all get this explanation? Is there anything you don't understand? If there is any question, please ask. Okay. I know this problem could look complicated, but it's easy. And when you see the code now, you'll see that it's easier than it looks. It's thinking more than coding. Okay. So let's here take the input. But I'm not happy with you not asking anything in this problem because I'm sure that you have questions in this problem. Okay. So please, if you have questions, ask me while I'm coding, for example, anything. So here I'm taking an integer n, and then so corresponding to the number of nodes, and then n minus 1 lines corresponding to the edges and the value for each edge. Okay. But now I said that I actually the construction of the tree doesn't matter. Okay. So whether tree looks like this or so whether a tree looks like this or looks like this or anything, it won't matter. Okay, because I am always sorting the values of the nodes and the values of the edges and constructing them the way I said. So it won't matter the actual shape of the tree. Okay, so I'm not interested in considering the actual edges of the tree. Okay, so I know that I have n nodes and n minus 1 edges, but the problem gives us, so the input is giving us the actual edges, but I won't be considering them. Okay, so I just take them, so I'll just take the edges as an input, but I won't consider them. Okay, I won't store them. So here in time CNN, and then for n minus 1, I want to make an array A of size n and B of size n minus 1. And then I want to loop n minus 1 times to take the edges, right? So normally I would make something like that. Like the last problem, I think the last problem, I don't remember, but normally I make something like that, and then add the edge x, y to the graph. But I'm not considering any edges now. So I'll just take the value of b, right? So I'll just make this and then take b of I. But why store extra two variables while I'm not using them? So why not just taking b of I 3 times? Okay, that's okay. So I'm taking b of I, then I'm taking b of I, then the last time I'm taking the real value of b of I, because I'm not considering the first two values which corresponding to the edge. Okay, so let's make this smaller. Let's loop for each x in b, for each number in b, and then just take x 3 times. That's it. And after that, I want to take the values of a. So that's it. I took a and b. Then I'll jump to the solution. So now we want to do binary search. Let's first store our answer. Nothing is stored here. Okay. So for binary search, left So the smallest value would be 0, and the largest value would be n minus 1, right? Because at most I would change n minus 1 values, which are all the number of nodes corresponding to the edges. Okay, so r equals to n minus 1, and then while else more than or equals to r, mid equals l plus r over 2. So now this mid, let's call it x. Okay, so this x is the number of changes I want to make now. Okay, number of coins. So x here is the number of coins I'll check now. I want to verify is x if x is available or not. So as I said, to make that, I'll shift. So I'll make 2 pointers, int I and j. So j will always be 0. Okay, so j corresponds to b. To we'll check in b, and I. So I want to shift it by exactly x, right? So I will be x. So if x equals to 0, then I will be also equals to 0, and I won't shift anything. But if x equals to 1, then I'm not checking the first element of A with the first element of B. I'm shifting I with 1. Okay, that's it. So let's make it here. I equals x, and I'll not declare j here because I'll loop here for j. J equals smaller than minus 1, j plus plus. Okay. So now I'm looping for every element for b. I'm just checking it with the corresponding element in A, right? So let's make a Boolean value here equals true. And I'll make this false whenever a condition is not met here. So kn equals. So what's the condition? The condition is A of I greater than or equals B of j, right? So if this is not true, then OK will be ended with 0, with false. So OK will be false. Okay, but there is another thing. I'm saying here that j should be smaller than n minus 1, but also I should be smaller than n, right? Because I shouldn't cross n, and that's it. So now if OK, so if this number of changes is OK, then I want to check a smaller number of changes, right? Then I'll make the right equals to middle minus 1. So I'll go to check to the lower half. Okay, but else if it's not okay, then I'll check to the upper half, then mid plus 1. But first, after seeing that this number of changes is okay, I want to set the answer to x. So answer will be equals to x, right? Because it's okay. That's it. Actually, that's the solution. Small binary search with 10 lines.
Probably we should also sort A and B before going to search.
Yes, you're right. I always forget that. Okay. Okay, yes, that's true. So now I sorted A, sorted B, and then come for the binary search. Let's check this. Not comma, so I should make and. Okay. And also I should increase I every time.
Increment I.
Yes. So notice that I didn't increment it here. I made it easier to increment it here. But what does it do here? So when doing I++ like that, it actually takes, so a of I is the value of I before incrementing. Okay, but if I did like that, plus I, then a of I will be the value of I after incrementing. Okay, here's the difference. So I incremented after taking the value of it. That should be it. Let's check, and of course print the answer. Let's check it.
Just to clarify, the answer would be the answer stored in left variable, right?
So what do you say again? Your voice is.
The answer would be stored in variable L, right?
No, the answer would be stored.
Okay, got it.
Answer. Okay, yep. I'm updating it every time.
Sure.
Okay. Where is mid?
It's X actually. The mid is X.
Oh yes, actually. Okay. So I'm just checking the last time before submitting because codechef takes a long time for judging a solution. Meanwhile, if you have any questions in the code, please ask, okay? Okay, that should be okay. Let's submit it. Hope there is no small bug. Okay, accepted. So here is the link to the solution. Actually, this is not the link. Here is the link. Okay, I finished today. Thank you, everyone. Do you have any questions before I leave? Okay. Bye, everyone. See you again.